introduce ma'am, because she is my colleague. Like ma'am joined in Usman University in 2006 after completing her ME from Andhra University, sorry, Tirupati University, right? And prior to joining here, she has already had experiences in a state government irrigation department. After that, she joined here, and then she is very passionate about the subject. And then, whatever she wanted to, she will start from the beginning actually, and she became associate professor 2 years back. And she has very good knowledge about on the metallurgical part, especially where we are also combinedly doing this work on the workability analysis of even of some projects also. And we are very sorry for just giving a very small brief introduction about ma'am. Please, ma'am, I can carry out.
Thank you very much, madam. Thank you, Professor Saraswatama, madam. Thank you.
Ma'am, excuse me, ma'am.
No problem. There is not much to
Excuse me,
introduce.
ma'am.
Okay, I'll continue with my talk. Shall I?
Ma'am, excuse me.
Srividya, no need.
Excuse me,
No.
ma'am. Can you hear me?
I can hear you, but already Saraswati madam introduced me. I don't think it's required.
Ma'am, you can continue, ma'am.
I will continue. I will continue. Dear participants, a very good morning to you all. I will be sharing my PhD work, that is on workability and hot deformation behavior of metastable beta titanium alloys. So this work consists of 2 parts. Okay, one part is on workability at room temperature. The other part is on evaluation of hot working behavior. So the working and the second part with the respect to hot working. So so we all know that during cold working there are a lot of dislocations, that is the dislocation density is increasing, thereby the material will become very hard to further strain it. So that is why after sometimes we cannot further work on the material. So we have to see the workability, how much the material can be worked at room temperature or during cold working. So that is given by a property called workability. Okay, it is not a property, it is just a parameter called workability. So see, there are 2 terms. One is formability and workability. Workability is with respect to bulk materials and formability is with respect to sheet metals. So as I am working with respect to the bulk materials, so we are dealing with workability. So workability is nothing but it is the ease with which the materials could be formed without any defects or cracks. Okay. So workability, as I told you, it is not the property of the material. Okay, it is just the parameter which we are interested to find out. So the workability, the factors which affect the workability are the ductility of the material, because it is the workability is nothing but it refers to the fracture resistance. So the fracture resistance is directly related to the ductility of the material, and the ductility is again related to the microstructure of the material. And also not only it is dependent on the material, the workability is also affected by different factors like temperature at which the material is being worked out, the strain rate that is applied on the material, and the deformation process, whether we are going for rolling or forging or extrusion, what process we are working. And not only that, it also depends on the workpiece geometry and also on the lubrication conditions. So there are many parameters which affect the workability. So what we can do is we can keep some of the parameters as constant, and we can just check the workability of the material by using a diagram called workability limit diagram. The other name for workability limit diagram is nothing but the fracture limit diagram, because workability is the term which is closely related to fracture. So how this workability limit diagram has come into picture, we'll see. See, workability diagram or workability limit diagram or fracture limit diagram, it depends on a ductile fracture criteria. Just I will read out and then I will explain what is that. Ductile fracture criteria. This is the ductile fracture given by the Atkinson. According to this criteria, it states that there exists a unique correlation between the tensile fracture strain and compressive fracture strain for a given material at room temperature. Okay. So first we'll see, I will just explain this one. See, we have a material here. So when you are compressing the material, it undergoes two types of strains. Okay. It will undergo circumferential tensile strain and compressive axial strain. So it is undergoing the circumferential tensile strain, that is called as the hoop strain, and it is undergoing the axial strain. So the body is subjected to two types of strains. So when this body is undergoing such deformation, okay, it undergoes usually a non-homogeneous deformation. So when it is undergoing such non-homogeneous deformation, so I told you that the deformation also, the strains that the body undergoes also will depend on its geometry. So why we are interested in geometry is, as we are changing the aspect ratio, the fracture conditions also will change. So it may undergo brittle fracture, it may undergo a mixed fracture, or it will undergo a ductile fracture. So as we change the aspect ratio of the component of the part, the fracture conditions also will change. So for a given material at room temperature, if we keep changing the fracture conditions, and if you are plotting all those fracture strains, okay, this y-axis is the tensile strain and x-axis is the compression strain. Okay, if you plot all the fracture strains for different fracture conditions, they have seen that all these fracture points are forming a straight line. That means there exists a unique correlation, means there exists a slope, that is a slope between the tensile fracture strain and compressive fracture strain for a given material at room temperature. So this line will help us. This line we call it as, so when we join all these points, this line we are calling it as fracture limit line or workability limit diagram. So this line helps us in many ways. So what are its applications, we'll see. So we'll go to the applications and we'll see how this fracture limit diagram will help us. So now we'll take one example. We have a bar with us. So this bar, I'm subjecting it to some compressive forces and some riveting operations. Say some riveting operation has taken place, and this bar, say it is of a. Before that, I want to tell one more thing. See, these lines are all touching the fracture points. That means what? If the material is strained above this line, that means it will surely fracture. If material is strained below this line, that is material is safe. So it is a limiting line. Above this line means material is unsafe. Below this line means it is a safe domain. Means below this line we can strain the material. Above this line we should not strain the material. Okay. So keeping that in mind, we'll go for this. So here, when we are subjecting it to the compressive stresses, some riveting operation you take. So it is undergoing two types of strains. One is the circumferential tensile strain and one is the compressive strain. So let us say during this operation, the material undergoes a maximum tensile strain of this much. Say this is the line which the material will undergo. And we have assumed that this material is of material A, and this is the workability limit diagram for material A. So this purple line which we are seeing is the workability limit diagram for A. See, now you can see that when we have used this material A, it is crossing the see, this horizontal line is the maximum or the limiting the strain which we have given to the material. Okay, so when we are using the material A, we can see that it is the limiting strains or the maximum or the threshold strains the material is undergoing is falling under unsafe zone, because the area above this line is unsafe and the area below this line is safe. But here we can see that the maximum strain it is undergoing is falling under unsafe zone. That is, we cannot use the material A. So we have shift to another material which have good workability. So when you are going for a new material, that is the material B, we can see that the limiting strain, see this is the horizontal line which is called the maximum strain the material will undergo. So this maximum strain, that is the maximum tensile strain, is falling below this blue line. So below this blue line means it is a safer zone. Above this line means it is an unsafe zone. So it is falling below this line. That means it is a safer zone. So we can shift to a material B and we can do this cold working operation. So there is another method also for doing this, not only shifting the material. So material shifting is a little bit costly. Apart from that, we can do one more thing. That is, we can change the strain path. Strain path is nothing but the strain the material is undergoing, the way the material is being strained during the entire process. So this is the strain path for one process, and this is another strain path. So if this strain path we can change by two ways. We can change the processing method, okay, the way which we want to form the material, okay, we can change the forming method, and we can change the lubrication conditions. So if we change the processing method, we can see that the slope, see the blue line and red line. So here in the blue line, for example, we'll take that it is non-lubricant condition, and red line we say it is a lubricant condition. So when you are going for a lubricant condition, we can see that the strain path is different. So this by using this strain path, we can see that the limiting strain falls in the safe zone for the material A itself. So we can still use the material A and we can still safely work out by just changing the way it is being processed. That means by using this workability limit diagram, we can independently work out whether the process is suitable for the material or not, and also whether the material is suitable or not. So we can independently consider the process and the material parameters in both quantitative and qualitative form. So in both ways, we can check by using the workability limit diagram. So in this way, though we know that the workability limit diagram workability is not a property of the material, it depends on so many parameters. Still at room temperature, see this discussion only holds good for room temperature workability only, because at room temperature only that ductile fracture criteria will work out. That is a unique correlation we can find out between the tensile strain and the compressive strain only at room temperature conditions. Okay, so this workability will work out only for room temperature working, that is the cold working processes. So here plotting this diagram is very simple, and a very simple test we have to perform to get this workability limit diagram. So that experiment we'll discuss. And before that, I have worked out on metastable beta titanium alloys. This is the material I have chosen for my PhD work. So as a case study, I want to show you. So mainly this titanium, like our steels, iron, it is a it exhibits a property called allotropy. Allotropy property means what? It exhibits one metal, it is exhibiting two different microstructures. Okay, that is called allotropic nature. So some materials in nature will exhibit, like iron, titanium, cobalt, and nickel. Some elements will exhibit such nature. Here in our for titanium also it exhibits HCP structure up to a temperature of 883, and above 883 it exhibits a BCC structure. So BCC structure we call it as beta phase, and HCC structure we call it as alpha phase. Okay, this is for pure titanium. So the transition temperature will change as we keep adding the alloying elements. So like steels, as they exhibit a different allotropic nature, so we could make different types of steels. Likewise, here also, as titanium is exhibiting this allotropic property, we could make different type of titanium alloys. That means we can add the alloying elements which will stabilize this alpha phase even at high temperature, and even we can add the BCC beta stabilizing elements which will stabilize the BCC even at lower temperatures. Okay, so by adding these alloying elements, what they do is they will change this transition temperature. Okay, they will alter the transition temperature, so that why to get BCC structure means BCC structure, if you go, it is more, we can work on the material easily. The formability is more, but HCP, we know it is a very hard and brittle structure. So depending on our applications, we can either go for alloying with alpha or beta. So if you are alloying with alpha stabilizers, so alpha stabilizers are mainly aluminum, gallium, and nitrogen and oxygen, and beta stabilizers are vanadium, molybdenum, and chromium. So if you are adding alpha stabilizers and you are getting the alpha microstructure even at higher temperatures, we call it as alpha alloys. And if you are adding both alpha and beta stabilizer elements, and we can see both the phases, it is called as the alpha plus beta alloys. And if you are adding the beta stabilizing element, approximately 30% of weight, so that we can see even the beta phase at room temperature, those alloys we call them as beta alloys. And my work is on metastable beta alloys. Why we have taken this alloy is, here the beta alloying elements are added in the ratio, in the weight percentage of 10 to 15%. But here we are using a term called metastable. Why metastable means, so though we are getting a beta phase is a high temperature phase. Okay, though we are able to get the beta phase at room temperature, but it is metastable. Means if you give time for it, if you age it, again the alpha phase will try to precipitate in the beta matrix. So this precipitation process actually will give the strength and hardness to the material, like precipitation hardening. Okay, this is one of the mechanism which we give the strength and hardness to the material. So here my work is on beta. Already these beta alloys are discussed in detail by the scientists from DMRL, so we'll not go into it, but we'll mainly focus on workability and hot working behavior. Okay, so these are the alloys. I have taken 2 alloys of the, okay, we'll focus only on titanium 553, which is a metastable beta titanium alloy. And I have subjected it to 3 different heat treatment conditions, though the alloy is same. By subjecting to 3 different heat treatment conditions, we can clearly see how the properties are changing. Okay, here you can see the as we all know that by annealing process, that is furnace cooling, the material will usually become soft. But in this case, in our material, it is the strength of the material is increasing. Why? Because during furnace cooling, we are giving enough time for the alpha to precipitate into the beta matrix, because we know that it is a metastable phase, metastable beta alloy. So the beta will not remain as it is. So slowly the alpha phase will try to precipitate into the beta matrix, which is giving this much strength to this material. Okay. Why we have taken these 3 conditions is to just check the workability. 3 different conditions we have taken, but we mainly focus on workability. So we now came to a conclusion that we have to plot a workability limit diagram. For plotting the workability limit diagram, we need to do one simple test called the simple compression test. We have to perform at room temperature. Okay, so here we can use any press, any single acting press also is okay. So what we have to do here is we have to press the material till it get cracks, and we should not continuously press the material. We should press the material in intermediate stages. Means we should compress the material in intermediate stages, because we should, at every time after little compression, we have to take it out and we have to measure the hoop strain and the axial strain, and then keep it again, and then again measure the hoop strain and axial strain. Okay, till the material gets fractured. So why we are doing this is we want to see how the material is being strained throughout the process. Okay, and I told you that the workability limit diagram is drawn for different fracture conditions. So to get different fracture conditions, what we are doing is we are going for different aspect ratios of the workpiece. We are changing the different aspect ratios, that is H/D ratios for the samples, so that we will get different fracture conditions. Okay, let the material fracture by any way. Workability limit diagram gives the safe zones and unsafe zones. So we have to look for all the different modes of fracture. So for that is the reason we have gone for different H/D ratios to generate different fracture conditions. Okay, so after we have to just keep the material and we have to keep measuring so we have taken different H/D ratios. You can see that different diameter and different height, different, because each material will fracture differently depending on its H/D ratio. So these are the strain path curves generated for the same material subjected to different heat treatment conditions. So these strain path curves are nothing but, here y-axis is hoop strain and x-axis is axial strain. Means this is the circumferential tensile strain and this is the compressive strain. So how the material is being strained through the entire process till it gets fractured is given by a path called strain path. And for workability limit diagram, these fracture strains are enough for us to draw the workability limit diagram, but the slope of these curves will have a major role to play, that we'll see. So the fracture points, if we plot all the fracture points for all different conditions, if we plot, we'll generate a workability limit diagram like this for all different fracture points. If we are plotting, many points are overlapped. So if we are plotting all the fracture conditions, the fracture strains for all different fracture conditions, we'll get a workability limit diagram. So we have generated workability limit diagram for 3 conditions: air cooling, furnace cooling, and aging condition. And we have seen that for air cooling, the workability is better compared to the other 2 conditions. So the data, I told you, the data which we get from strain path curves. So for drawing the workability limit diagram, fracture strains are enough. But while the experimentation is going on, we have taken the strains at each intermediate stage. So by using those strains, we have plotted these strain paths. So the slope of these strain paths, we can use it for estimating the stresses the material that it will undergo. See here, biaxial stress it will undergo during compression. That is the circumferential stress it will undergo, and it will undergo the axial stress. So these stresses we can estimate using the slope of the strain paths. Beta is nothing but the, see, we can see it is a hoop strain divided by the change in hoop strain divided by the change in axial strain. So the slope of that we can use. These are the relations that are already available. So we can use these relations to calculate the stresses the material is undergoing during the process. Okay, so we can calculate the axial stress and circumferential stress and mean stress. So, and we can plot the stresses. Okay, these y-axis is stress and the x-axis is strain. So the material is undergoing the axial stress, that is the compressive axial stress, and the tensile stress, circumferential tensile stress. Here we can clearly see that when the compressive tensile stress is more, the material is fracturing at an earlier stage. So the strain it is undergoing is very little. So as the tensile stress is more in the material deformation is limited by the tensile stress, means it is cracking earlier. Okay, so the values that are given are correct. And we have worked on 3 samples, so we can see the factorography studies we have done, and we can clearly see that in air cooled sample I told you in air-cooled sample, we got good workability, and mostly in air-cooled sample, the fracture mode, you can see there is this total dimples are there, which represents that it is a ductile mode of fracture. And in furnace-cooled sample, we can see a lot of flat facets, which indicate that it is a brittle mode of fracture. And in aging treatment, we can see both the flat facets and the dimples also, which indicates mixed mode of fracture. So a simple test we can perform at room temperature, and we can plot the workability limit diagram. And also one more thing, without doing the experiments, even we can simulate the process also. But when we are simulating the process, the finite element programs, they will check our material with respect to some ductile, they will simulate with respect to some ductile fracture criteria. So these finite element computer programs, what ductile fracture criteria they adopt, we have to see, because there is no unique fracture criteria that is suitable for all materials. Okay, so there are many ductile fracture criteria that are proposed by the scientists, but we have to check their validity before using them into our finite element computer programs. Whether it will suit our material or not, we have to see. So there are many ductile fracture criteria that are available, depending on different assumptions. We have Frundal fracture criteria, which is under an assumption that whenever the total strain energy to fracture reaches a critical value, then crack will occur. Okay, this is based on that. And Crockfit model, this is based on the assumption that whenever the tensile strain energy reaches a critical value, then fracture will occur. Okay, these are the different assumptions by different scientists. So whether these assumptions will work out for our material or not, we have to see. So Brozov criteria, here we can see that here they have adopted a stress function which will consist of both the maximum tensile stress and the mean stress. And when this function reaches a critical value, then fracture will occur. This is the assumption of Brozov. And Woho and all, they have assumed that the ratio of the maximum tensile stress to effective stress, when it reaches a critical value, then fracture will occur. So these are the different assumptions, and there are many more. Apart from it, there are some 20 to 30 different new fracture criteria that are already there. But we have considered these fracture criteria, only 4 we have considered, and we have checked whether which fracture criteria is suited for our material. And using these, I told you that the slope of the strain paths can be used not only for calculating the circumferential stress, the biaxial stresses, it can be also used to estimate the theoretical fracture strains the material will undergo. Okay, so by using these equations, we can calculate the material constants, and then we can use those material constants to generate the theoretical fracture strains. So once the theoretical fracture strains are generated by these criteria, we can check with our experimental values whether the theoretical strains generated by these fracture criteria and whatever the experimental fracture strains we got, whether they are same or not. We can check by plotting the relative error curves. And from these error curves, we can see that the Frundal criteria, the variation with respect to the Frundal criteria is very high. Means there is a large variation between the theoretical and the experimental values. So we cannot incorporate this Frundal criteria in our finite element programs. So we can use the other criteria which are giving a variation of plus or minus 15%. Either Crockfit or Ohetol criteria we can use. So we all can, this is a simple area, we can easily work, everyone we can work by using just a press and with no dice also not required. If we have a single acting press also, it's enough. We can plot the workability limit diagrams. And for different treatments, because we know that the workability limit diagrams are related to the fracture, and fracture in turn is related to the ductility of the material, and which in turn relates to the microstructure. So we can subject the materials to different microstructures and we can plot the workability limit diagrams. Thereby we can check how the workability is related to the microstructure also we can check. Here we have checked the effect of volume fraction of alpha on the workability of the material. And we have seen that as the alpha volume fraction increases, the workability is decreasing, because alpha is nothing but our HCP phase, that is hexagonal close packed phase, which is a very hard and brittle phase. So as this phase increases in the material, the workability decreases because the ductility will be poor. So the workability is decreasing. So it's a very simple test. We can work it out in our labs. And the next part which we are dealing with is hot working part. See, in cold working, what will happen is in the microstructure changes, so what will happen is only the dislocation density will keep on increasing in the microstructure, and as the dislocation density is increasing during cold working, the material will be strain hardened and we cannot further work on it. Okay, but when we go to the hot working process, there is a total different phenomena that is happening in the microstructure. Okay, because here, and also one thing in cold working, the strain rate sensitivity is very less. Whatever strain rate we use, there is not much change in the flow stress. The strain rate sensitivity is very, means we cannot, there is not much strain rate sensitivity during cold working. But when we come to hot working, strain rate sensitivity is a very important parameter, because as we increase the strain rate, the flow stress also increases. Okay, so here we have two major factors, that is the temperature and strain rate. And the phenomena that is going inside the material during hot working is also different, because here as it is thermally heated, the thermal heating will activate the phenomena called recovery and recrystallization, because hot working is nothing but working above recrystallization. So here the two phenomena will occur, that is recovery and recrystallization. We'll actually see what is recovery and recrystallization, and then we come back to this. And according to this, and not only this, because of the because different strain rates we'll be using and different temperatures, so we'll be processing the material under non-equilibrium conditions. Thereby, it may undergo some microstructural defects also, like flow localizations, shear bands, deformation bands, and cracks. So here, why we are checking into the hot working behavior is, here we are trying to optimize the process parameters like temperature, strain rate, and strain, so that we can generate sound forgings with increased production rate. So we cannot increase the strain rate because to increase the production rate, and we cannot increase the temperature and all to get more strain, because along with the good phenomena, that is the stable phenomena, these defects also will occur internally inside the microstructure. So we have to see on which domains, I mean the range of the process parameters where we can get the sound forgings. That domain we call it as a stable domain. So before going to all this, we'll just recap about recovery and what is recovery and recrystallization. Though you all know it, just I am interested because you may not be interested in my work. So we'll just go through the recovery and recrystallization. So first we'll see what is recovery and recrystallization, and then we'll move on to the case study. So the material that is in hot working, the material is undergoes the two phenomena called dynamic recovery and recrystallization. Why we call dynamic means during working the material is undergoing these phenomena, so that is why it is called as the dynamic. So just we'll recall what we know about recovery and recrystallization, and then we'll go to the case work. So in cold working, we know that during case working, the dislocation density increases, thereby the strength of the material increases, and we cannot further work on the material. So we'll anneal the material. So when we are annealing the material, the two phenomena will happen, that is recovery and recrystallization. So we are providing some thermal energy for these things to happen, and also the stored energy, which is in the form of dislocation density. So these two, recovery and recrystallization phenomena, happen during annealing. So what is recovery, we'll see, and the driving force behind recovery. So the driving force behind recovery is the stored energy, which is in the form of dislocation density. Always the material want to lower its energy. See, in Guru Vidyarthi's lecture also we have heard that whenever the material has low energy, it is a stable region. Okay, always material, whenever we try to whenever it is frees its energy, it will always try to free its energy so that it can come to a stable state. Okay, so recovery is the phenomena where it will release this energy, which is in the form of which is stored in the form of dislocations by a process called recovery. And recrystallization also, it usually takes place at a little higher temperature compared to recovery, and afterwards it will further tries to lower its energy by decreasing the number of grain boundaries. We'll see one by one. So what is recovery? It is a process by which deformed grains can reduce their stored energy by the removal or rearrangement of defects. So we all know that the dislocations are the primary reason for the deformation of the material, and it is trying to during recovery, it is trying to annihilate the dislocations. What I mean by the dislocations is, see here we have different dislocations. Blue one we can call it as positive dislocations, and red ones we can call it as negative dislocations. So due to the thermal energy or the energies due to the thermal activation and all, these dislocations can move. Okay, and when the positive and negative dislocations combine, they actually make a full plane. Means, what is dislocation? It is only a half plane, but when these both will combine, they will make usually a full plane, and their defect will not exist at all. That is nothing but, if defect is not existing, it is nothing but annihilation of dislocation. Okay, so here we have it is trying to free up the energy by the movement of dislocations in such a way that the dislocations are annihilated. So the density, the dislocation density is decreased. You can see during the recovery process, the dislocation density is decreased, and also these dislocations are arranged in an array, in a pattern, in an array, in an organized way. Okay, thereby it is trying to get to a stable state. So this process is called recovery process, and here the dislocation density decreases, but much changes will not happen in the microstructure. Only thing is the dislocation density is decreased and the dislocations are arrayed. And now we'll go to another process called recrystallization. So recrystallization is nothing but, it is a process of formation of new strain grains, strain-free grains. Now the grains which are being nucleated are strain-free. Okay, and the driving and the thermal energy that is given will help the material to undergo this process. So the driving energy for recrystallization is the stored energy in the material. Okay, in the form of it is mainly the whenever the material undergoes cold working, that material is much suitable for recrystallization purpose. So here recrystallization is a, so we can see that here we can see that the new grains, the new strain-free grains are forming at the expense of old grains. So the new grains are formed by eating out old grains. These are the strained grains, and these are the new strain-free grains. So when these strain-free grains are growing, this process we call it as recrystallization. So this happens during hot working and also during the annealing process, because we are providing the thermal energy required for the movement for this process to occur. Okay, and further grain growth also will happen. Here the grain boundaries are more, here the grain boundaries are less, but due to the grain growth, means it will try to further decrease its energy. It will free up the energy, it will come to the lower energy state, because grain boundaries areas are higher energy state. It will try to come up to the lower energy state by grain growth. So this is the process that will happen during recrystallization. And why we are discussing about recrystallization and recovery in much detail is, and also one more thing is, recrystallization temperature is not a unique temperature. It all depends on purity of the material, and also how much the cold strain, or it is strained before this process undergoes. That it all depends on many factors, but this is of major importance for us, because here you can see during cold working the material strength is increasing, but here you can see the ductility is decreasing. See, we'll focus on only two curves. Remember, here we are focusing only on the blue curve and the solid red curve. Okay, the other two will not discuss. Only we'll focus on blue and red curve. So during cold working, we can see that the material is undergoing, whenever the cold work, the material strength is increasing. That is called as the strain hardening. Okay, but the ductility is decreasing. But during recovery, we can see that there is a very good increase in ductility. Okay, why there is a very good increase in ductility? Because here the dislocations are annihilated. Okay, are annihilated, and because the resistance to dislocation is not there, most of the dislocations are annihilated and they are arranged in a proper order. So in a proper order, so that the moment of dislocation is easy. So the ductility is increasing, but the strength is remaining same. Why the strength is remaining same is the rate of annihilation is equal to the rate of production of dislocations, because the working is still occurring. So the material is still being strained. So when the material is still being strained, again the dislocations will keep on generating. But the rate of generation of dislocation is equal to the rate of annihilation of dislocations. Thereby the stress will remain constant. Okay, that is the reason why the stress has become constant during this stage. Okay, but once the material is going into recrystallization state, here we can see the ductility is further improving, but during recrystallization the strength will decrease. Okay, that we have to keep in mind. And also this ductility improvement will help to work upon the material, will help us to work upon the material, and the decrease in strength will help us to work easily on the material. So recovery and recrystallization are very good phenomena, so that we can easily work on, still work, we can do the plastic deformation further on the material, okay, with less force because of decrease in strength, and also because of the improvement in ductility. So these two phenomena are very, very good in hot working process. So in hot working process, if these two phenomena are happening, means it is in our process parameters are in stable mode. Okay, so this is why we have discussed in depth about recrystallization and recovery. So now we'll actually move to our hot working. And in hot working, we know that because of the thermal energy we are providing, these two phenomena will happen. Okay, and apart from that, I told you that as it is a non-equilibrium process, it is a where the strain rates and temperatures, we can give different strain rates and temperatures, and also instabilities also may occur. So we have to always search for the optimum regions where these stable phenomena will happen. So now this is not of much importance for us. Just this will tell us that recrystallization temperature is a function of the amount of cold work, and it is also a function of the grain size, and it is also depends on the impurities and all. So we'll not discuss much on this. So we have seen that whenever this phenomena recrystallization and recovery happens, the ductility and formability of the material increases. Okay, we can easily deform the material with less force. So I told you that the good phenomena that are dynamic recovery and dynamic recrystallization. But here, as I told you, that strain rate has a major role to play. If you are going for higher strain rates, and the process is much in non-equilibrium conditions, and because of that, these instabilities also may occur inside the material, and we should see that these instabilities should be minimized or they should be avoided, like flow localization, shear bands, deformation bands, cracks. Okay, at the outer surface the forgings may look sound, but when we check the inside of the forgings, these phenomena would have been occurred inside the microstructure. Okay, so they will reduce the service life of the forgings. Okay, so that is why we should choose the domains such that these dynamic recovery and dynamic recrystallization will only happen. So such domains means the parameters, the process parameters, we should choose such that this phenomena will happen, the good phenomena will happen, and such that this bad phenomena will not occur in our material. Like that we have to choose. And mainly I told you the strain rate is very, very important, and the temperature and strain rates are the parameters which will play major role in the change in the microstructure of the material during hot working. So the hot working deformation response of metallurgical materials is strictly correlated to their initial microstructure as well as to the changes occurring during deformation at high temperature. So the initial microstructure will also affect the deformation. Okay, and also the changes. I told you the recovery, dynamic recrystallization, all this will happen during the hot working process. And the parameters which we should take control are temperature and the strain rate. Okay, and we clearly know that the high temperature deformation here acts concurrently with the other control parameter that is called as the strain rate. So these are the parameters which we have to take very much in control to control the microstructures that are occurring within the material. So to get the information about what is happening in the material, we should analyze the stress strain curves. Okay, stress strain curves obtained at different temperatures and strain rate levels. So if you analyze the flow curves, stress strain curves are nothing but flow curves. So if we analyze the flow curves which we have generated at different temperature and strain rate, this analysis will give a lot of information of what is happening inside the material during deformation. So that is why I am presenting a case study here where we went through the we tried to generate these flow curves at different temperature and straight lines, and we have studied these flow curves and how we could use these flow curves to give a lot of information. We'll see in further slides using a case study of my PhD work. So to generate the flow curves, we conducted tests called hot compression tests. These are isothermal compression tests. For that, we have conducted tests at 4 different temperatures. One is above the beta transverse temperature and 2 temperatures are below the beta transverse temperature. And we have chosen 5 strain rates. Okay, means the hot compression, isothermal hot compressions we have did at a particular temperature with a particular strain rate. Okay, so such tests, so total 4 into 5, 20 samples per one heat treatment. For one heat treatment we have conducted. And the sample sizes we have taken, they are very small samples only, and the whole test is conducted using a Global 3800 simulator. This is a thermomechanical simulator where we can maintain the constant strain rate. Okay, because a feedback loop is required to maintain a constant strain rate. So that feedback loop it is taken care by the Global simulator, thermomechanical simulator, and the keeping the temperature constant is also taken care by the Global simulator. So this machine is taking care of all the constant temperature and strain rate. So we should not worry about how to keep the constant temperature, and we should not worry about how to keep the constant strain rate. Everything is taken care of by the machine itself. So because of this machine, our work was done very easily. And after we have strained the material to about 60%, we have strained, and once the straining is finished, we have quenched the material so that to retain the deformed microstructure, we have quenched the material. And this is the setup. So one is a fixed joint, one is a movable jaw, and this is our workpiece. And this is the thermocouple, which will ensure, which is connected to the feedback loop so that the constant temperature is ensured. And we have, and by induction, by distant heating, we have heated the material, and the heating rate is at 5 degrees per second, and we have soaked it at a particular temperature. We soaked it for 180 seconds so that the entire material is uniformly heated up. And after that, we have conducted the compression stress, compression test up to we can give the strain, how much strain we want, we can strain it. We have given a strain of 0.6, so we have strained up to 0.6, and up to 0.6 we can strain the material, and the strain rate also we can control here. We have given the strain rate also here. The strain rate is given and the strain is given, and once the material has the particular strain has finished, the machine will automatically quench the workpiece, and we can take out our workpiece. So I told you that the initial microstructure will also affect the deformation behavior. So as a case study, we have taken two initial microstructure. One is the beta microstructure and one is the alpha plus beta microstructure. And this is the main important for us. So these are the flow curves that are generated by the machine. So here we can see the flow curves that are generated by the machine at different temperatures and different strain rates. So the red color, black color, blue color are different strain rates. So here from all the curves, we can see that as we are increasing the strain rate, the black color is 10 per second. As we are increasing the strain rate, the flow stress is increasing. And also we can see that as the temperature is increased, the flow stress is decreasing. Okay, that is the two major points, that is obvious only. And here we can see the, see, I told you in how the plots will look like during recrystallization and recovery, because here in I hope you have remembered here, because this information, that is why we went through recovery and recrystallization in much detail, because here you can see that during recrystallization the strength is decreasing. So if the flow softening is occurring like this indicates that some recrystallization is occurring there. And when the flow stress is constant like that, okay, it indicates it is in a, the material is undergoing recovery. Means it is a just a general understanding. It is not that it is a rigid rule. It is just a for general understanding. We usually assume that if the flow curve is after initial strain hardening, if the stress stress is constant, we consider it as a recovery region. And if the flow stress is decreasing with the increase in strain, then we consider that the material is undergoing recrystallization. So this is just a hint for us. Okay, you can just call it as a hint. So we'll come back to our work. So here you can see that there is a decrease in flow stress with increase in strain. So we can assume, we can just assume at the earliest, just initial stages, we can just assume that flow recrystallization would have happened during this region. Okay, and when the flow stress is constant, we can assume that recovery would have happened. Okay, these are just our assumptions, and we have to validate it with the microstructures, which we have to validate with the microstructures, which we have to taken by cutting the samples. Okay, the deformed samples at that particular temperature and strain rate. Okay, but before going to validation by optical microstructures, we can make a lot of use of the data which we generate from the flow curves. Okay, one way is we can make a mathematical model. We can use this data to generate a mathematical model. And also the most important thing and the most happening thing in hot working is processing maps. So we can generate the processing maps by using this data. So thus those processing maps are very, very important to us to study the hot working behavior. So we'll not waste our time in dealing with the mathematical models. Okay, because mathematical models always come with some assumptions, and here we use the Zener hollow parameter which correlates temperature, strain rate, and the deformation behavior. And we could generate the mathematical models that we can do. And they all come with some assumptions, and sometimes our experimental values may maybe they may be in close relation with the theoretical values as predicted by the mathematical model. But this is not of much importance for us. We'll just directly go with the processing maps, because this is the really thing that is happening. So we'll mainly go with processing maps. I think most of you know little about it. So that is why I'm going to directly to the processing maps. So what is processing map? See, here we have obtained a lot of data from flow curves. Okay, we can find out the strain rate sensitivity, we can find out the temperature sensitivity, everything we can find out by the flow curves. So once we get the data from the flow curves, we can plot a map called processing map. So what is this processing map? We'll see first. So this processing map is based on a model called dynamic material model. Okay, so based on this model, this processing map, once we generate this processing map, we can find out what are the stable domains and what are unstable domains. Here I told you that domains are nothing but the process parameters. So we can directly get what are the stable processing parameters. We can make the material to hot work, and we can also see the unstable parameters where we should not make the material to hot work. So that is given by the processing map. So how it will give? So what it is based on, we'll see. So it is mainly in this model, it will consider the workpiece as a power dissipator. So whenever we work upon the material uses the temperature will rise in the material. See here, this is the flow curve. And when we work upon the material, here you can see the flow stress and the strain rate curve, and the total power, the area under this curve is nothing but the total is nothing but the power, that is the flow stress into strain rate. So we can take the material as a power dissipator. Our component itself, we can assume it as a power dissipator, and it will dissipate the power in two ways. One, in the form of heat. Okay, the material gets heated up. So in the form of heat, it will dissipate the power. And the other thing is, it will dissipate the power in terms of the microstructural changes. Means it can use this power to make the material to undergo the microstructural changes. Means we can divide the total power, we can divide into two components. That is the power which is used for the microstructural changes and the power which is used for the heat conduction. So J is the parameter, the amount of the power which is used for microstructural changes, and G is the amount of the power which is being conducted in the form of heat. So if we can relate these two, if we can find a fraction, the how much is the J fraction with respect to the total power released, okay, how much is the J fraction? So dJ by dG, if you see the ratio of dJ by dG, it has come to it is almost equal to the strain rate sensitivity. So strain rate sensitivity is a major parameter which will tell us about the hot working behavior of the material. So it is a very important parameter for us, because the ratio of dJ and GJ has come about is approximately equal to M, that is the strain rate sensitivity. So after the total power that is generated, if most of the power goes in making the microstructural changes, then it is good for the material. Okay, and if most of it is being conducted away, okay, then it is not good for the material. So according to that, this material model has been developed. So the fraction of the power that is dissipated with respect to the total power, we call it as efficiency. That is called as the efficiency of power dissipation. So efficiency of power dissipation, it will totally rely on a parameter called strain rate sensitivity. So if this power dissipation is high, that means those domains are the domains which are favorable domains. Okay, they are favorable domains for us because most of the heat energy is used to make the microstructural to make the microstructural changes in the works. Okay, that is of use to us. Okay, so if we can, and also not only the efficiency factor, we can also they have also floated one more parameter called Zeta Factor. So this Zeta Factor is also function of strain rate and strain rate sensitivity. So this factor, whenever this factor is below, is negative, then it shows the regions of unstable regions. Okay, so here we have two factors. One, it is efficiency factor, and one is the Zeta Factor. Zeta Factor tells about the instability, and efficiency factor tells about the stable domains. So if you can include these two factors in one map, that map is nothing but our processing map. Okay, here we have included the superimposition of the instability map over the power dissipation map is nothing but our processing map. So this is the model they have already they are using for years together, for some 10 to 10 years, more than 10 years, and these process maps are working very good. Means they are almost whatever information we get from microstructures and the information we get from processing maps, almost they go hand in hand. Means this, the information given by processing map, we can actually believe it. We can actually, because why we can believe is because the M values and all values are the values which are generated from experiments only. Okay. So one case study we'll see here. So here I told you that whenever the efficiency is more, that is the safe domains, and whenever the Zeta factor is negative, that is a unstable domain for us. So these are the processing maps. I will just take one case study and I will tell you. So this is a processing map we have generated for our material titanium 5553 with alpha plus beta initial microstructure. Here we can see that the x-axis is temperature and y-axis is the strain rate. So these are our domains. So at what temperature, if you work at what temperature and what strain rates, the material is safe. And when you work in this instability, the shaded region is the instability region. So when you work in this region, the material is unsafe. Means there are possibility that some dislocation bands may occur, some deformation bands may occur, some flow localization may take place, some cracks may occur, anything may happen. So it is showing both the unsafe regions and safe regions. And in safe regions also, here we can see that the efficiency is 47% we are getting maximum, and in unsafe regions we can see that the efficiency is very, very less. Okay, it is not that unsafe efficiency less regions are unsafe, but they have derived a parameter called zeta. So where the zeta parameters falls in negative values, there they have taken it as a unsafe region. Okay, so now once we have generated the processing maps, we have to again check whether this processing map generated is correct or not. That we are doing by going for microstructural evaluation. So we have checked that for higher strain rates and at higher temperature range and higher strain rates. So these are the higher temperatures and higher strain rates. It is showing some instabilities. So we'll check whether the information given by processing map are correct or wrong by microstructural evaluation. So when we went for microstructural evaluation, usually at low strain rates, we have seen what we have seen are these are irregular grain boundaries we have seen, and small recrystallization grains also. See all these irregular grain boundaries and these elongated grains, these are typical of DRV. DRV means dynamic recovery. So the dynamic recovery phenomena is happening inside the material. So you see all these segregated grain boundaries, they indicate that dynamic recovery is happening inside the material, which is good for us. So there are the safe reasons. And but at higher strain rates, we can see some flow localization. See small new grains are formed, but they are formed locally. Here also you can see the new grains are formed, but they are formed locally. Not the entire structure is of small grains, small recrystallized grains, but these small recrystallized grains are occurred only at a particular locations only. Why this has happened is because we are working the material at a higher strain rate. So we have not given enough time. The entire process is a non-equilibrium process. So it would have happened that at some reasons only the material would have been heated up. Okay, some adiabatic heating would have taken place at certain points. Okay, and here for titanium the thermal conductivity is also less. So some amount of because of we didn't give the enough time for the heat to distribute throughout. So at some points only the heat would have been, some areas only the localized heating would have been happened, and here only in some localized areas only the deformation behavior is changing. So here such a condition we call it as flow localization. Means the flow is localized in some areas. See here in this area only we have seen the recrystallized grains. So when recrystallized grains are occurring in this area, that means what, the ductility is very good in these regions. That means what, much stress is not required for the material to undergo the further strain. So in see earlier we have seen in flow stress maps, when the flow stress is decreasing, so we'll quickly go because we'll quickly go to that point. See here we have seen that flow stress is decreasing with strain, and we thought that it was a recrystallization would have occurred, but actually what is happening here is the at higher strain rates, the phenomena that is happening at higher strain rate is not the recrystallization of the entire grain structure, but it is actually the localized recrystallization that is happening, which has led to the flow softening behavior. So flow softening behavior is actually generating has the defects. Okay, this we can not only by microstructures, this we can even see by using processing maps. So it is better to convert our flow stress data into processing maps, because the processing maps are relating well with the microstructures. Okay, instead of analyzing the flow curves, okay, it is good to analyze the flow curves, but after analyzing the flow curves, it is better to generate a processing map from the flow curve data. So at higher temperatures, we can see that it is showing an instability region. So this and the microstructure both are working hand in hand. So it is better to convert into processing maps and then check the validity of the processing maps using microstructures. So here we can see the flow localization is happening here and here, due to which the flow softening is taking place. But this flow localization is not good for us, because it has happened only in certain regions. Okay, not the entire region. That means it is an instability. Okay, and instability always tells us it is not a safe zone. We should avoid these zones. Okay, so from hot working behavior, I can only tell that because it is our time is also nearing. It is better for us to take the flow curve data and then convert that flow curve data into processing map, and we can use this processing map and we can validate these processing maps using optical microstructure studies. Okay, so these processing maps is very much used for almost we have almost a very huge book on processing maps. Almost they have developed processing maps for almost all the alloys. Okay, almost so because if you just go to the processing maps, it will give the safe and unsafe reasons, and they have even validated using the microstructures. So it is better to understand the behavior of hot deformation behavior using processing map, because processing map is going in hand with the microstructural changes, and that is better way of analyzing the hot behavior, deformation behavior using processing maps. And also not only the because there are so many microstructural changes that occur in during hot deformation. So sometimes the processing maps may also not give the proper information. So always it is better to check the go for the validate the processing maps using optical microstructures. So here also in one more case study also we have seen, and we have seen in the stable regions the recrystallization is happening, and also here we can see the segregated serrated grains, which is a indication of recovery. And here also we can see fine grains. It may not be clear here. So all equiaxial grains, these are all the safe zones for us. So if these phenomena is happening inside the material, means it is safe zones. Means these domains, these 900 degrees and 0.01 are domains. So these domains are safer for us. But when we go for higher strain rates and all, see here we can see that the flow localization is taking place. Not only that, not only the flow localization, cracks may come up, or some deformation bands may occur. So many are there. So many different types of instabilities are there. So all those may occur that we can see only by studying the microstructure. Okay, it will just the processing map will just indicate the instability. But what type of instability, if we want to check, we have to go for microstructure only. So without microstructure, we cannot see what type of instability it is. Okay, so I just try to cover the hard deformation behavior so that if anyone interested in this area, they may have a preliminary knowledge on this. And these are all our conclusions of our PhD work. And I don't think mostly they may not have much use for you. But the thing that is of use for us is how to work in the hard deformation area and how to work in the cold working area. So cold working area, we can work using workability limit diagrams, and hot working area, we can work using processing maps. So these two areas, this hot working area is always a green area for research. Okay, how much the people work in this area, always there is a scope for research in hot working behavior. Okay, so thank you one and all. I'm stopping my presentation here. Hope you could follow me. And if any questions are there, you can please ask. Already it is 1:15. I think I have taken a lot of time. Anything you want to ask, you can ask. Because it is our metal forming area only, our mechanical area. Though we have gone for microstructure, because everything we cannot, because nowadays everything is being overlapped. We cannot say that mechanical is different and metallurgy is different. So everything has to work in overlapped regions. Overlapping actually is good. Any questions you have, you can please ask. Because I'm from mechanical background only. We can happily work in this area if you are interested.
Dear participants, if you have any questions, you may ask Madam. Or else you can even type in the chat box.
I think it's already lunchtime.
Yes.
No problem.
Ma'am, thank you very much for enlightening your topic. It was
you.
very interesting, and you talked many things regarding the fundamentals of cold working, hard working, recrystallization, and recovery, right?
Thank you.
And also
Thank you.
processing maps, which are useful, and also the design and deformation processing of metals. So thank you so much, ma'am.
Thank you. Thank you. Thank you, Srividya. Thank you. Sir, stop here. I'm stopping here, Srividya.
Hello, hello, madam. Hello.
చెప్పండి.
Good afternoon.
Good afternoon.
This is Pati, ma'am.
Sir, చెప్పండి సార్.
I think how to decide the crystallization temperature material
Sir, voice is breaking, sir. Can you type in chat box? Voice is breaking.
Recrystallization is different for different material. So how to means understand how to in correct position, what are the parameters are there? How to understand the recrystallization temperature for different materials. Any parameters are there? Any properties, madam?
The problem is your voice is breaking. I could not get your question. The only thing is you can type in chat box. We can share the information.
Okay. Okay.
ప్రాబ్లం ఏమంటే వినపడట్లేదు సార్, మీది వాయిస్ బ్రేక్ అవుతుంది. మీరు చాట్ బాక్స్ లో పర్లేదు, వాయిస్ బ్రేక్ అవుతా ఉంది సార్, అర్థం కావట్లేదు. ఓకే, if you want you can type in chat box. I'll try to answer. Okay. If you want to post question in chat box, you can post. Srividya, I think we can stop.
Okay, ma'am.